Consensus algorithms have a reputation of being notoriously difficult to understand. There are two sides to this story. One is mathematics, a formal proof of correctness of the algorithm of consensus. The second part is pragmatics or engineering, building an actual real-world distributed system which is correct and fast. This divide is evident even in the history of consensus. The paper which solved consensus in the presence of network partitions was published in 1988 by Brian Oki under the supervision of Barbara Liskov. This paper introduced the view stamp replication consensus algorithm, but it did it as a part of a larger data management system. And it was primarily an engineering paper. The famous Paxos paper by Leslie Lampert was submitted at 1990, and the Paxos paper stripped down consensus algorithm to its bare essentials to reveal the mathematical beauty of the thing. Although mathematics is motivated by engineering, and engineering would have been impossible without the underlying mathematics, trying to understand the two at the same time is where the difficulty of understanding consensus stems from. So in today's lecture, I want to focus on the mathematics of consensus. And I'm going to explain consensus using the language of set theory. In a sort of alchemical transmutation, we are going to turn Led Zeppelin into golden earring. We take anyone who understands the basics of set theory and turn them into someone who understands consensus. I'm Alex from TigerBeetle, and this is my colleague Tobi. And conveniently, Tobi knows the basics of set theory, but doesn't yet understand consensus. So, Tobi, are you ready to be transmuted into someone who understands consensus?
Always ready.
Okay, so let's get started. And the way we will do this is that we aren't actually going to explain consensus. You know, like most mathematical books are written backwards. They start with theorems, and after a theorem follows the proof. But in reality, when you do mathematics, you actually start with the proof. You study the problem until you understand it. And the theorem is actually the very last step. So what we are going to do today is that we are going to construct a consensus algorithm with our bare hands using trial and error method, fixing all the errors until we have something working. But before we start with that, I would like to define a species of mathematical animals which we will be studying. So what we are going to study are discrete systems which evolve over time. So in general, let me wipe the whiteboard. So we are going to have some large state space S. And there might be some states, like, you know, S0 belongs to S. So this is like the state space of a system. This is a single state of our system. And our system evolves discretely with time. So that means that we are going to look at the sequence of state. S0, S1, S2, and Sn, and then infinity. So this is an infinite sequence of state where each state is from our overall state space. And this infinite sequence of state is called a behavior. And the branch of mathematics which we will use to study consensus is essentially a study of behavior. So this is an example of the animal which we will be studying. And like right now, it's kind of like super abstract and super confusing. So let's make a very concrete example of the system. So we'll say that Okay, let's state. So we'll say that, hey, the state of our system is just a set of natural numbers. And our system is essentially a single variable, a counter, which is a natural number. So state is just a counter, which is, let's use programming notation here. Counter is a natural number. So a behavior of the system could look like c equals 0, then like c equals 1, c equals 2, etc. Or it could be like, c equals 0, c equals 0, c equals 0, etc. Or actually any other sequence of natural numbers. Tobi, is it clear so far?
Yes.
Okay. The problem, though, is that, we might want to describe different counters. We could have a counter which describes natural numbers, or we could have a more general counter which is like monotonically increasing, or maybe monotonically decreasing. And we kind of like, from what we have, we could speak about like any behavior of a system with a counter, but we don't have a way to specify a behavior of a particular counter which works like in some particular way. Like, maybe it like counts only prime numbers or something. So let's do this. I want to specify the behavior of a counter which oscillates between 0 and 9. So it could increment or decrement by 1, but it never goes beyond the 0 and 9. The way we do this is that we specify the initial state predicate called init. And let's say that in the initial state, we start with counter equals 0. And then we specify the state transition predicate, step. So what we are going to do here is that we have like a certain value of counter in like state here, and I want to describe what is the possible value of counter in the next step. So I'm going to do it this way. I will say that C prime is equal to C plus 1 and C is less than 9, or C prime is equal C minus 1 and C is greater than 0. Okay, yeah, so
this should be an OR, right?
Yes, this should be an OR. Thank you. Yeah, I was going to teach you some mathematical notation, but it seems like you already know it. So
you said OR, but
yeah,
you wrote and.
Yeah. So mathematical notation. This is the way I write and. Like normally people also write it as like the ampersand, like the pretzel, but I cannot draw an ampersand with my hand, so I'm using like this simple like inverted V sign. And correspondingly, the OR is like the normal V. Okay, so what is C prime? So this step function is a predicate on a pair of state. And C is the current state, C prime is the next state. So what this says is that if C is less than 9 at the step I, then at the step I plus 1, C is equal C plus 1, where we take C from the previous step. And the second thing is that if we are greater than 9, then we reduce the C by 1. So that's kind of like the key thing. If we draw like the diagram, S1, S2, S3. So this C refers to, say, S2, and this C refers to the state in S3. So if we look at the behavior of the system, so let's give an example behavior. we start with c equals 0, right?
Yeah.
Then we need to find what c could be equal here. We look at the let's look at the second clause here. We have here and c is greater than 0, but our c is equal 0. So this one definitely we cannot take this path. So we have to take this path. And it says that, OK, c is equal to 9, and then c prime must be greater than 1. So we go to c equals 1. OK, on the next step. Well, now, actually, both branches here are valid. We could either say that c here is equal to 2, or we could say that it goes back to 0. So we have inherent non-determinism in our system, consistent of the counter, and that is actually fine. So I want to stress that those things here, init and step, they are not functions. They are predicates. So you take one state, another state, and then check if the predicate is true for these things. To make this more obvious, let's look at the example where like the predicate nature of this thing is like super obvious. Let's say that we still are working in a system where a state is just a counter, but our init is going to be just true. So we could start with like any value. And our step is going to be c prime. Well, no, let's say c is less or equal than c prime. OK, Tobi, could you give me an example behavior for this system?
An example behavior of, I can start with any counter basically, right?
Yeah.
I can do c equals 10.
Yeah.
And now I check if the predicate is true, and which is true, right, for step.
Yeah.
So I can, for instance, be like this. That is the next one. 70? No, or 10.
Oh, 10 again, OK. Yeah.
Right, and then I can do I can arbitrarily jump, right? Basically.
Yeah. Yeah.
So I can do 5. Oh no, I can sum up 70.
Yeah. OK.
Or 80.
Yeah.
90.
OK, that's great. Now, could you give me example of a state of the sequence which is not a behavior of this system?
Going down. Like, for instance, if I'm at 80, I cannot go back to 5.
OK, yeah.
I can only grow monotonically.
Yeah. This is correct. So we've learned to specify behaviors of a particular system. So this is kind of like a Sladen counter, and this is monotonic counter. Essentially, we have this, like, the whole set of possible behaviors, and we carve out some subset of them, and we say, OK, these are behaviors of our particular system. And the way we do carve out is that we specify the init and the step predicate. And we're using this like prime notation to succinctly express the predicates on pairs of state. OK, so now what we would like to do, having specified the behavior of a system, we would want to specify, to basically say if our system behaves as we want. The way we do this is that we specify the second predicate, which kind of like describes the set of good behaviors. So
just to recap quickly, right? This init is not a function because it's a predicate, and you can set basically you evaluate if it's true or false.
Yeah. So we could like write a type of this thing. So init.
But if I write here false, then I cannot. That will not be.
That is a system without behaviors.
Yeah. Okay.
Yeah, which is like valid thing. So the type of init is that we take state and we return a Boolean saying like, hey, is the status correct or not? And the type of the step is that we take a pair of states, and we return a Boolean. Okay, so yeah, and I'm going to mix like the set theoretical notation and like the functional programming notation. So now I want to specify like now which behaviors I consider correct for our system. And let's say that what I want from my system is for the counter to never exceed 9. So the predicate, how would I call it? Well, I mean, let's call it like CP, correctness predicate, is going to look like this. I would say that for every I, Ci is not less than 0 and not greater than 10. So this notation, Ci with I as the superscript, means the state of a system at a particular step number I. So you know, like C prime is like the next one relative to C, and Ci is just like, you know, C0, C2, C1. So probably, yeah. Okay, so this formula here, it carves out a different set of behaviors from our system than this formula. So for example, here we could have behavior like 0, 5, 9, 8, 1, 6. And all behaviors are infinite. While in this formula, like this behavior is actually not possible, because here we can jump only by 1.
So the state transitions that you modeled here are actually not valid, right? In the behavior of this particular system. They are valid in this correctness predicate.
Yeah.
But not possible.
Yeah, yeah. But what is true is that every behavior here satisfies this condition.
Yeah.
And this is kind of like, you know, essentially like the example of the kind of statement we want to prove. We say, hey, good behaviors are behaviors where the counter is between 0 and 9. And we say, hey, we have this particular counter which like increments and decrements by 1. And then we say that, hey, every behavior here also satisfies this predicate. So essentially, we have like this our entire space of all behaviors. I think it is spelled in mathematics as omega power. So like S omega is the set of infinite sequences of elements of S. In this whole set, we specify one predicate, which is like our good behaviors. And then we specify another set, which is like I don't know, system, sys, let's call them traces.
And in our example, that would be like...
Yeah. And what we want to say, like the theorem we are trying to prove, is that actually that the picture looks like this. That every behavior of our system is actually a good behavior. And this is like example, the system, the theorem. And now you see, we actually have to prove this fact that every behavior of the system satisfies this predicate, because it is like easy but non-trivial observation. And the way we do it is, could you like sketch the proof here?
No, I want to ask something again before that. Why do we need actually this thing? Why can we not directly prove that this is the sequence and behavior that we want? Why do we need this more powerful correctness predicate to prove that all these transitions are within this thing?
So the reason is that this specification is in some sense implementable. It is algorithm. You kind of like say, okay, if my C is less than 9, then I increment it by 1, or if it is greater than 0, I decrement it by 1.
Yeah.
This, in turn, is an axiomatic specification. Like, it doesn't tell you how you compute C prime given C. It tells you which states about it, but it doesn't tell you how we are going to compute. So this is where kind of like mathematics meets engineering. What we actually can implement is this style of specification. But our correctness criteria is actually going to have this form. And we would ask a question like, hey, does our implementation actually match our specification? Okay, I guess you could also see similar style of reasoning in, like, programming language theory when you prove that your type inference algorithm indeed gives you the types which make every expression check out. Okay, so how we are going to prove this statement? We are going to prove this statement by induction. So this statement says, hey, for every I, where I is a natural number, and when we see for every natural number statement, our first instinct is to use induction. So we say, okay, induction base, when I equal 0, our initial state must be between 0 and 9. And our initial state is 0, so that is good. And then we prove induction step. We say, okay, suppose we are in some state which is between 0 and 9. Would the next state be between 0 and 9? And then you say, okay, if our C is equal to 9, then the next step is going to be this one, so we go to 8 and it's correct. If it is not less than 9, then like, yeah, whatever. So basically we do some case analysis, and then we say, okay, quod erat demonstrandum, что требовалось доказать, how we used to say this in Russian, the theorem is proved. Okay, so this is kind of like, honestly, the most important thing I wanted to tell you today. Because once you understand, like, how the mathematical animal we want to study looks, you could then go and understand the consensus algorithm. And if you don't have this like set theoretic understanding of what consensus theorem even means, it might be hard for you to understand things. Okay, Tobi, so are you ready to go and do the actual consensus now that we did the prep work?
Let's try.
Okay, let's try. Okay, so what is consensus? I'm going to start with the predicate. Like specifying what consensus means. So, like, hand-waving consensus is that we want to select a particular answer such that there is no ambiguity. That there is like only one option selected. So we need to have like some, okay, example problem. Let's say we have like a building with a roof which stores bicycles. And we would like to choose the color for this building. So we have a set of choices, which consists, well, let's say it's like red, green, and blue. And we want to choose a single color. So how do we model this? The state of our system is going to be the set of colors which we have actually chosen. Now let's call it like the outcome. So we have like outcome, and it is a subset of our choices. So this is like functional notation, and mathematical notation would be that outcome is a subset of our choices, which is like the same. Is notation familiar? So this is power set, the set of all subsets of C. And we say, hey, kind of like O is some subset of C. And this is like essentially the same thing, like spelled out directly. O is a subset of C. So we could have like, you know, like O0 equals to empty set, and then we can have like O1 equals to like red, and then like O2 equals to blue. And this is bad. This is not consensus, because we made our decision. We said, OK, we are chosen red. But then on the next step, we say, no, 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 wait, wait, wait. We are going to choose blue. So we want to say that, hey, this thing is not possible. If we chose any color, then we stick to our guns. It's useful to invert this and say it positively. So if we chose a color at a one step and a color at a different step, those colors must be identical. So our, well, let's call it like a theorem, not correctness predicate, like theorem. Like the consensus theorem is that for every I and j, if a particular color belongs to outcome on step I, okay, I think let me write it more beautifully. So consensus theorem, CD. For every I and j, if C1 belongs to outcome on the state E, and C2 belongs to outcome on step J, then what I'm writing here, Tobi?
What does this mean now exactly, I and j? These are arbitrary times?
So,
steps?
So our state is O, but this is like state at a particular point in time.
Yeah.
So our behavior is a sequence of those O's.
Yeah.
O0, O1, O2, O3. So this is the state at the step I, and this is the state at the step J.
Yeah. And they should be equal, right?
I
mean, that would be the correct theory. But if we make one decision at this point, we also want.
So you want to write that like OI equals OJ. This is not entirely correct, because we start with no decision. Our initial state typically would be like O0 equal just an empty set. Empty set. Let's use empty set notation, because like, you know, we start and we don't yet know which color we are going to pick. So there's going to be some decision problem, and at some point we pick a color, and from that point on we stay.
Okay. So we want to have a valid color out of this first, and then we want to maintain that decision. Yeah.
So we say, let's finish this. We say, okay, so let's take two states at time I and at time j. And at time I we have one color there, and in time j we have a different color there. And if this is consensus, we must guarantee that C1 is equal to C2. So like, you know, like as a mental check, let's say that like OI is like red and OJ is red. Then this works. Like, you know, here we have only red and here we have only red, and they are equal.
Yep.
If we have an empty set and let's say blue, this also works, because we don't have any C here. So this is trivially true, and the implication is also trivially true. And if we have something like red and red-blue, then kind of like, if we pick red as C1 here and red as C2 here, this part actually works, like, you know, red equal to red. Yeah. But we, okay, I think I'm actually missing quarter. So we want to say for every C1, C2, we want to say that for every color in OY, and for every color in OJ, they are the same. So for red and red, it works, but it doesn't work for red and blue.
Yeah.
And therefore, it doesn't work. So this is important. Like, this is like our intuitive notion of consensus. We start not knowing the answer, and then we arrived at the answer. How we model this mathematically? We say that our answer at a given moment in time is a subset of possible answers, which makes sense because we expect to start with an empty answer and arrive at a singleton set which contains just one element. And we capture this intuition saying that there is always only one element at the set by saying that, hey, if we look at our answer, if we make a snapshot of our answer at 2 points in time, and at the first point in time we have like a color in there, that color must be in the second answer set as well. Okay.
Can you explain this again? Here, these two steps, why this holds?
These two steps. Because we want to say that for every pair of colors, such that first color is here and the second color is here, the colors are equal. So what is the set of pairs which such that the first element of the pair is in this set and the second element of the pair is in this set? It is an empty set because this set is empty. So like product of empty set and the set containing only B is also an empty set. So we want to say that for every pair, something holds. And because there aren't any pairs at all, this holds vacuously. And this is important, and like, we say like, for all, and not like, that exists. Because if the quantum was the existence, like, there exists pair, we would say, no, that's false because, okay, the pair doesn't exist. But because we say, hey, we want for all, then we get a vacuously true statement.
I think I vaguely remember now. You basically could also write it here like empty set, comma B, right? But you just ignore the empty set because it's in every set.
I mean,
and that's basically the same as this one, right? You basically have the empty set in there. Or what do you mean?
Not exactly. Like this. Well, we could write the right one as a union of an empty set and B.
Yeah.
But it is not a set of an empty set and B, because like it's an empty set.
Okay.
So that's different.
No,
But that goes into like slightly fancier set theory where we say, hey, this is 0, and this is 1, and this is 2, and we are not going there. Although I would love to, but no, we are not going there today. Okay, so. To like maybe give like some examples, let's like actually show like some behaviors, some specific behaviors. So we start with like an empty set, and then we go to the empty set, and then we go to the empty set, and then we go to blue, and then we go to blue, and like infinitely we continue with the blue. Again, this is all correct. We pick two indexes. If one points into the empty set, we have 1 because we don't have any pairs. If we pick both points where there is only B there, okay, we also 1 because there is only one pair. We need to consider B and B, and B and B are equal. And kind of like if we had, I don't know, red here, then we've lost. So this pair works, this pair works, this pair works, but this pair over here doesn't work. Okay, so do you understand the mathematical?
Not quite, I think. What I don't really understand is why you can go back in your decision to empty.
This is just arbitrary behavior.
Yeah.
So
why
just
is this correct in consensus?
So this is because we don't require it to be incorrect, and this is actually true. So like you might decide And this actually is even true in the real consensus. So you might have some number of machines which arrived at certain log in your replicated state machine. But then every machine crashes. And while all the machines are down, you don't actually have the log. The set is empty. But then they start again, and they should start with the same log. So it actually is okay. Yeah, let's write this down, because this is like non-trivial thing, and this is important. That this sequence, where we have alternating empty set and a single set containing only R, is also valid according to our definition of consensus. We don't necessarily require that we always have a value chosen. Actually, I mean, in the algorithm we implement, we will have this property that, like, it's always going to be R, but you could say, hey, like in a real system, we will relax this a bit and say, okay, if no one's online, we could actually have this empty. So this is practically the difference between the system which says, okay, if you have 2 out of 3 nodes online, you have consensus, but if you have 0 nodes online, all bets are off. From the system where you say, okay, if you have 2 nodes online, you have consensus. If you have 0 nodes online, you don't know the answer. But if you then again have 2 nodes online, if they go back up, then you get the same answer as before. And this is why like this language of set theory is useful for thinking about these problems, because like this like really crisply captures this very real distinction between the systems.
So in other words, the second thing you mentioned, right, would be if you have blue here, that would be okay under some definition of consensus, right, when all bets are off.
So if you have like black here, blue. Yeah, if you have black here, it's like that doesn't type check. If you have blue, I mean, like it depends. It wouldn't work for our definition of consensus, because we say, hey, this is red, this is blue. But you could imagine a different definition where it works, like, you know, like eventual consistency, like, you know, maybe. Yeah, actually, okay, we could do eventual consistency. So in the eventual consistency, our like consensus theorem said that, like, you know, for every E and G, the eventual consistency theorem, yes, it would say that there exists certain number n such that for every E and G, such that J is greater than n and I is greater than n, and then like the same thing.
Yeah.
So like in consensus, we say that, okay, for every state, we like know the answer. Eventual consistency says, hey, like there might be some inconsistencies in a finite prefix of our behavior, but starting from some point, we get to consensus. Yeah. And also, it kind of like doesn't really tell you what the n is. So that's kind of like, you know that eventually it will be consistent, but if at any given point in time, you don't actually know whether it is consistent or not. Okay, so that was our theorem, a thing we want to prove about our system. Now we are going to implement some systems which hopefully obey this definition. And we'll start with like super like simple, the most straightforward consensus system possible. We say that the initial state is that the set of answers is just an empty set. And then we say that the step function is, well, O prime is equal to O, or let's say O is equal to empty set, and O prime is a subset of our choices, and the size of O prime is equal to 1. So new mathematical notation. Okay, Tobi, you are a champion. Okay, so on every step, we either can maintain our choice, or if our previous choice was an empty set, then we could choose one value.
Yeah.
Like new notation here, like set modulus is just the number of elements in the set, which is like 1.
Yeah.
Okay, so this is kind of like very simple implementation of consensus, where we make a decision and then we stick to it. And again, the fact that this thing implements consensus also needs to be proven, because our consensus predicate says that, hey, for every 2 states which might be arbitrarily far off, something holds. In our step predicate, we only relate 2 states which are next to each other. So if we were to prove consensus theorem for this system, the proof would go something like this. Okay, let's prove by contradiction. Let's assume that consensus theorem doesn't hold for this system. Therefore, there exist 2 indexes, I and j, such that the sets at I and j are contradictory. The next step we are going to do is that we are going to prove if there exists some I and j which might be different, like I here, j here, and like there's like, you know, like 1 million steps between them. There must exist some pair like I don't know, star and like j star, which are like next to each other, where there is also a contradiction. And we kind of like, you know, do like, okay, let's say that this is, okay, let's say this is a contradiction. Let's do a step here. So either this pair is a contradiction or that pair is a contradiction. So we like shrink this thing until we get to 2 neighbors which are contradictory. And then we take a look at our step function and say, hey, actually this is not possible. So okay, do you understand like how the system works?
I mean, how the step function work or the proof, like the contradiction stuff?
Okay, so the proof you don't really like need to like fully understand.
I think I understand.
Yeah, so like you could,
Yeah,
okay, you could draw, okay, could you give me an example of behavior of this system?
Of this one?
Yeah.
So we start with empty set.
Yeah.
Right, and then we go to the next step.
Yeah.
Where we basically say, okay, if we are empty set, we go into this one, and we choose 1 color out of our all colors that are available to us.
Yeah.
And we choose only 1 set, for instance, R.
Yeah. And the next step?
Is the next step to maintain the choice that we did before.
Yeah.
So we should never forget what we.
Yeah. So it's going to be like R ad infinitum. Okay. So how we solve consensus? Is it really that easy? Well, not quite, because like we could, again, this is an algorithm actually. You could implement it as a program. Like, you know, you roll a die, make a decision, and then stick to it. But the problem is that this system is not going to be available. If your computer crashes, then like you don't have a decision. And if you restart, maybe you forgot what you have chosen. And while you are crashed, there is no possibility to know the result of consensus. So we are going to make this distributed. We want to say that our state is not like a singular outcome, but actually like a pure process state. And somehow we need to arrive at consensus. So okay, let's start with the simplest possible thing. Let's say that we have 3 people, like you, me, and Chaitanya over there, and we want to select a color for this building with a roof which stores bicycles. How would you do this? Like the most simplest possible way to...
We vote.
Yeah, we vote, and the color which gets most votes wins. Okay, let's try to specify this idea using the language of set theory. Okay, we'll need, so this is like going to be like the list of our sets. We have sets of searches. Now we grow the set of processes. So let's call them like P1, P2, and P3. So you are P1, I am P2, and Chaitanya is P3. Now, we vote. How do we model this in a state? So we say that we have like votes for every process. P1 votes, P2 votes, P3 votes. And we say that we have like VP. And a vote is going to be a subset of choices. So when I draw an index, a superscript, that means I'm talking about a state in a particular point in time. When I do a subscript, that means that this is just like a bunch of variables. Okay. And here it is P, so it ranges over P. We actually have like VP1, VP2, VP3. So we say, okay, everyone like has a vote. Then we have init, which probably says that, hey, we are undecided yet. So like, you know, like implicitly, like there is like for every P, VP equals 0. And then we have a step function, which is going to look exactly what the consensus formula looked like, because like, you know, voting is deciding and is like solving consensus for yourself. So we say that like VP prime is equal to VP, or I've almost done this again, or VP is an empty set, and VP prime is a subset of choices, and kind of like I actually don't have to write this thing because it's like, you know, follows from our definition of VP, but well, doesn't harm. And the size of VP prime is equal to 1. So this is voting process. Each of us three have a set of votes. We start with an empty set of votes, and then on every step we could cast our vote for a single color. Now, the fun thing is like, what is the predicate for the outcome? So we just describe the votes, but it's not clear what is an outcome. And let's define it, like outcome by definition, what it equals to. So outcome is when a certain color receives a majority of votes. So outcome is going to be a set of colors such that it receives a majority of votes. So I'm going to write a certain set here, which is like the set of votes, and I will require that it is greater or equal than 2. So outcome is a set of colors such that the number of votes for this color is greater than 2. So what is this set of votes? Well, it is the set of processes such that the color belongs to the votes cast by this particular process. Okay, so once again, the outcome is the set of colors such that the set of processes that voted for this color is greater or equal than 2. I think this is relatively straightforward. Do you get it?
Yep.
Oh, okay. So what can we say about this algorithm? Well, first, it actually, again, implements consensus. Like you see, I kind of like said, hey, like consensus is not notoriously difficult to understand, but we like specified like 2 algorithms, and they both actually implement consensus. So it's like something. Am I tricking you? Well, we'll see it. And again, like to prove that this actually implements consensus requires some, like proof by induction. But like it's see like that like if one because like we only require voting for a single color. Like if some color reaches majority, then no other color can reach majority. So okay, that's good. Consensus works. Do you have a question?
Yeah, I have one question actually. Can you explain how this outcome relates to this stuff? Because you could basically, we start with empty set, right?
Yeah.
Then we vote, you get red, Titania gets blue, I get green. That is not a majority vote.
Yeah.
So we go now in the step, right? And
Yeah.
we are not the empty set anymore.
Yeah.
And we still have this basically, right?
Yeah.
How do we try again? Like which kind of, then we need to invoke outcome, which basically says there is no outcome reached, and then we go again with the step, or how does it work?
I mean, outcome reached is just going to be an empty set. So let's say that we start with like with this set. So this is like V.
Yep.
And the outcome. And the outcome here is like also empty set.
Yep.
And then on the next step. Okay, yeah. Okay, so I guess I'm going to erase this because like the actual formula is not as important. The important thing is that like every process votes and you can get to vote for a single value.
Yeah.
Okay, so now let's do an example of behavior of the system. So we start with 3 empty sets.
Mm-hmm.
And then we go to an empty set, red, empty set. And then we go to empty set, red, blue. And then blue, red, blue. Okay, so so we have 1, 2, 3, 4 steps.
Yeah.
What are the outcomes? Like by definition, so outcome 0 is empty.
Empty set,
Here.
Empty set.
Here.
Empty set.
Empty set.
And here blue.
Yeah.
What if here is like green? Then still empty set?
Yeah, this is something if this is green, this is going to be an empty set. And
then what happens then?
And this is exactly why this doesn't quite solve consensus fully. But we'll get to that in a moment.
Okay.
In fact, actually, let's temporarily pretend that our set of choices is just 2 colors,
Okay.
Black and white.
Yeah, so we have by necessity a majority.
Yeah. And here, I would let's actually do a real experiment. So right now we all are here at Cape Town. Soon we'll get to our respective countries. I will go to Portugal, Tobi will go to Germany, and Chaitanya will go to USA. So let's do this. We'll soon have Halloween. So at midnight on Halloween, each of us will think about either black color or white color. What will happen? Well, by definition, we will reach consensus because like there's going to be like a majority color. So like at the same time, no one of us will actually know what is consensus because we're like at the different like places on Earth. We actually have to call each other to understand what consensus is. So this is another like important thing which set theoretical thinking helps you realize that consensus is a property of the entire system. An entire system might achieve consensus without any participant actually realizing that. Okay, and now let's go to Tobi's example. what if our state is red, green, blue? Well, this is like bad, because this is obviously like, outcome is empty set. What's worse, the system is completely stuck. No matter how many steps we are going to take, the system isn't going to reach consensus. And that's why this algorithm here doesn't exactly work. So in a real consensus theorem, we actually have two clauses. We have correctness clause, safety clause, which we've specified, like, if you pick two values, then they are consistent. We also have a liveness clause. And the liveness clause says that, hey, if you make a finite number of steps in your system, and you are in a certain state, then there is some continuation which gets you to consensus. And here we don't have this continuation. So we also could like explain this using the language of set theory, but it gets like slightly complicated because we need to think about infinite sequences and then like finite sequences, so scalar notation. So I'm not going to do that. We will kind of like keep this liveness property in mind, but we will be reasoning about it informally. But yeah, this is kind of like a problem. Our democratic voting procedure can get stuck. And this, again, also nice connection between mathematics and real life, because in a real world parliament, in a democracy, you also could get in a situation where the parliament is basically stuck because there is no clear majority. The parliament is really divided about a particular issue. So, okay. How are we going to fix this issue of our democracy getting stuck?
So we could retry. Like if I see that that's all about the robot system, right?
I mean, but
all I do it randomly. That's also fine.
I mean, but we could still. Hey, I want red, I want green, I want blue. Yeah, let's not do this way. Let's kind of like continue this like analogy of like democracy. What could work better than democracy? What isn't prone to a deadlocked parliament? That is autocratic government, where you just say, hey, we are doing this, and like you don't really have a choice. So, well, I mean, like that's actually how autocracy used to work like a while ago. In the modern world, we actually have something tense here. So it is not true that in autocratic regimes you don't have elections. You certainly have elections. The trick is during the election in an autocratic regime, you only have one option you can vote for. So that's kind of like nice. You have elections, but at the same time, like there is guaranteed winner. So how we are going to model this thing? Let's say that we have still have like these choices, these processes. We still have votes, but we say that P0, well, P1 is actually like the autocrat, the king. So for step function, for V0 is going to be like V0 equals V0 prime, or oh dear, I just cannot do this, or like what we have written before, or like V0 is equal like empty set, and V0 prime is 1. For everyone else, we will require them to vote as V0. So we say like V1 is equal V1 prime, or V1 equal an empty set, and V1 prime equal V0. So process 1, okay, off by 1, I said 0 here. Okay, so let's say that P0, P1, P2. V1 runs like the normal voting thing, and everyone else, they kind of like do the voting, but whenever they vote, they have to vote for the same thing that V0 voted for. So this is like a nice mathematical model of another government system, autocracy. And it indeed has this advantage over democracy that you cannot get a stuck parliament, that the decisions are always made because there is like only one option which you could decide. But again, there is this problem with autocratic regimes in that when the leader becomes indisposed for this or that reason, the procedure to elect a new leader isn't really defined. Like power transitions in autocracies are literally undefined behavior. So if we try to code this system up, that will mean that like if this node dies, we either become unavailable or we can pick someone else to be the leader. But that kind of like sounds a lot like consensus. And if we don't do this with consensus, we might end up like, with split brain with like two leaders at the same time. So, okay, where are we at? We are trying to build a system which is an algorithm which can be implemented by distributed system, which gives us consensus. We tried democracy, and the problem with democracy is that you could get stuck if there isn't clear majority vote for a particular value. We tried autocracy, which cannot get stuck for this reason, because everyone votes for the same value, but which can get stuck if a particular node, which is currently the primary, the leader, the dictator, is offline. Okay, Tobi. So imagine you are designing a constitution for a country, and like you haven't listened to consensus lecture so far. You know that hey, democracy has its benefits and like autocracy has its benefits. Is there some way we could combine those two? And actually, if you are watching this on YouTube, this might be a good moment to pause the video and to ponder this question, like how you could combine those two systems, because this is going to be only one of the only two non-trivial steps that we are going to do on our path to consensus. So, Tobi, any ideas?
So, as long as we have a leader, we basically adopt the scheme.
Yeah.
But if we don't have a leader, we need to start voting again.
Yeah, but how do you know if you don't have a leader? That's consensus.
Yeah, exactly.
Yeah,
yeah. To find out that
yeah. So there is like this like brilliant insight. We let everyone to be a dictator for a day. So we are going to have 3 separate votes. So let's see. We are going to have processes here. So it's like P0, P1, and P2. And we are going to have votes here. Let's use the V0, V1, and V2. And P0 would be the primary for this vote. P1 will be the primary for this vote. And P2 will be the primary for this vote. So, and they all kind of like happen at the same time. So, like maybe first P1 wants to do a vote in V0. And it looks like, okay, no one's voted. I'm not a leader of this vote, so I have to stick with my like empty vote. So it like sticks with empty. And then maybe P2 decides to vote in V2. And P2 in V2 is like, okay, I want to pick red. And then P0 wants to vote in V2, and it's like, yeah, like I really want to pick blue here, but I can't because I am not a leader for this vote. So it like goes and picks red here. But on the next step, like P0 is like, oh, I really want to pick like blue here, but I cannot. But I can pick blue here, so like, we get blue here. And then maybe P1 says, okay, so now I know what my leader wants to vote for, so I'm going to do blue here, and maybe, well, I don't know, let's do blue here. And then maybe P2 like does blue, and yeah, like here we just don't vote, or like vote for something else. It doesn't matter. So this is kind of like the system. Now, like we used to have like a state of votes pure process. Now we actually will have like V P V. So for every instance in time, for every process, and for every vote, we have a set of votes. And actually, to make this more fun, I'm going to make this table infinite. I'm going to say that after V1, we have like V3, and V4, and etc., etc. And like similarly, like we can kind of like continue to use like modulus to specify who is a leader for which vote. So that's how you get the benefits of democracy and dictatorship. You say that anyone gets to be a dictator infinite amount of time. And like when you are a dictator, you could dictate what you're voting for. And when you are not a dictator, well, you still can vote. It's kind of like democracy. But well, you gotta vote for what everyone else has voted for. Okay, so why? Well, first of all, before we like study this table, do you understand how this works? Yeah, and I'm not going to write formulas here because the formula is going to be like, I mean, it's actually pretty fine. It's not like too horrible. So if you like, write in like VI, you could actually type this all nicely in LaTeX, but the space is limited, so I'm going to stick with pictures. But yeah, so we understand like this like table. What's cool here is first, any particular vote cannot get stuck due to a split vote because there is only one value that we are choosing in a particular vote. So we like either reach majority or we don't reach majority because someone hasn't voted. The second interesting property is that while an individual vote can get stuck if a particular process doesn't make any steps, if it is disabled, but as long as we have majority of the processes who make steps, there is some vote that can complete. Yeah. So that's kind of like cool. Our system is available. There is only one problem here.
How do you advance these things, right?
What?
How do we advance these numbers? Like, how do we make sure
that
everyone...
I mean, we don't really advance them. That's the thing. They are happening concurrently at the same time. So you could, like, P1 can first vote in V4 and then vote in V0. So this is actually going to be like important, and this picture like gives a false intuition. It kind of like feels like the time flows from left to right. But this is not true. All voting happens concurrently. And we could say like first ballot 4 starts and stops. Then we do V0, it starts and stops. And then we do V1 and V2 concurrently. And then maybe like, V like 1 million, and then like everything in between. So, okay, the problem is, what's our O here? Like how we say like what is the set of values we have decided upon?
We always need to look at a certain vote, right?
Well, I mean, we can do different things. So, but what is kind of like the simplest, most like dumbest possible way to extend this definition to this table? We could say that the value is chosen. The value is an outcome if it is chosen in any particular vote. So we take this definition of outcome and we say that like, exists like vote V such that if we look at the votes in like particular vote, then we have a majority voting for that value. So this is like mechanically valid definition for outcome. So like if we look at this table, so I think like if you look at this table, the outcome here is actually like B chosen here, or here, and R. So this is like the outcome for this table, B and R. Is this clear?
Yeah, but you only want one, right?
Yeah, kind of like, yeah, it kind of like mechanically works, but now we see that, hey, this isn't consensus, because we have chosen two values at the same time. And by the way, actually, this is kind of like fun thing which I glossed over. When we specified a correctness theorem, we said like, hey, for every I and j, something, something, we never actually said that I and j must be different. So a weaker form of consensus theorem, it says that like at any given point in time, you select only one value. And this doesn't work here. Okay, so that's kind of like a problem. How do we fix this? Well, again, as we have been doing like so far, let's actually fix this in a brute force way. Let's kind of like just say that, hey, we never ever want this to happen. And we only need to figure out just how we can achieve that. So let's do a nice big table. And try to make it work. So, okay, we have like P0, P1, P2. Okay, I think I'm running out of blue, so let me switch to black, because yeah, now we are getting serious. We are going to black. Okay, and we have like V0, V1, V2, V3, etc., etc., etc. So we somehow want to make sure that our outcome actually obeys consensus, that we never ever going to select two values. How are we going to solve this? Well, I will do it simpler, like using the trick we've been doing so far. I will kick the can down the road. So Tobi, let's say that you are P0. So you are primary for this vote, and you are primary for this vote. So Tobi has a crown. So, and let's say you haven't yet voted in this round. So you gotta choose which color you put here. And okay, we want the outcome to be consistent. So your task is to choose red, green, and blue, red, green, or blue value, such that you personally are not responsible for any inconsistencies that might arise. So if, like, you know, someone says, hey, like this and like these cells are contradictory, like, you know, this selects red and this selects blue, like that's fine for you, it's not your problem. On the other hand, if someone says that, hey, like this one and this one selected contradictory results, well, that's your problem, and you want to avoid it. Yeah. So you need to choose a color such that you do not conflict with these folks and with all these folks. How would you do this? You think very carefully, because you have like infinite possibilities for doing it wrong, because there's going to be like infinite amount of votes. Sounds kind of hard, doesn't it?
Kind of, yeah.
Kind of hard. So okay, I will make your problem infinitely easier, because we actually are all on the same team. So if I am P1, when I will be voting here, I will also be thinking about not conflicting with any votes to the left or to the right of me. And let's say that every one of us only votes, cares about votes to the left of us. So when you pick a color here, you try very hard not to step into contradiction with any of these ballots. Yeah. When I'm voting here, I'm thinking very carefully about not stepping into a contradiction with this set of votes. But neither me nor you think about votes to the right. Because, like, okay, we could still have a problem. You know, Chaitanya is here, and could we have a contradiction between like this vote and Chaitanya's vote over here?
If you forget.
Well, no, because we also require Chaitanya to execute the same algorithm. Yeah. So, okay, we made our problem infinitely easier. Before, we were thinking, how could we avoid conflicts across like this entire table, which is infinite, which is kind of hard. Now we only need to care about a finite subset of the table so that we don't have conflicts there. Okay, so how do we do it?
So when I voted here?
Yeah. Let's say that the table is completely empty. Okay. No one voted anywhere, and you decided to vote in V3 first.
Okay, then I choose green. I can choose any arbitrary.
Yeah, you could choose. Yeah, you could choose green. But then, like, you know, if here, like, you know, this chooses red, and this chooses red, and here someone, like, you know, also chooses green, that's a problem.
Bad, yeah.
Yeah.
Now I need to choose red because this leader here dictated basically red.
Yeah. But
I want to make sure that we don't conflict.
Yeah, but I think he's like, you know, he might like what you're looking at is an empty table.
Yeah.
So like, you know, you chose green, and then later, this guy over here, he chooses red, but he only cares about votes to the left.
Yeah.
So kind of like doesn't work. So here comes the second idea. Which gives you consensus. And again, if you're watching this on YouTube, this is another good opportunity to pause, take a walk in the park, take a shower, and to think about like how we could make sure that whichever value we select for a particular vote, this value is safe. It will never contradict any values in the votes to the left. And yeah, thank you. I was going to say with the votes before, but again, repeat, there is no time here. These are votes to the left, and they can happen earlier or later than the vote over here. And actually, when they happen later, it actually is a problem because we don't know information. Okay, so what could you do here? Well, you could pick Chaitanya and say, hey, Chaitanya, you are going to vote in my vote, in vote number 3. And I forbid you from voting in any of the previous votes. So you could force Chaitanya to say, to commit to not voting here. And you yourself also commit to not voting in any previous rounds. Yeah. Now, if you pick green, you know that your bacon is saved because none of these votes could complete. They never reach a majority. And like if Alex here decides to vote for red and like Chaitanya votes for red, like there's going to be a contradiction. But like it's Alex's problem, it's not yours, because we kind of like agreed that everyone cares only about the votes before. Okay, so actually, like if the table is empty, that's good. So what happens if like you try to do the same thing? You try to ask Chai not to vote in any of the previous votes. But Chaitanya said like, oops, sorry, actually, I have already voted for blue here. What do we do in this case?
Then I should pick blue actually, right?
Yes.
To not mess it up.
Yes. You could say, okay, Chai, that's fine that you voted for blue here. I still require you to not vote here. And I myself commit to not vote here but in my vote or view, I am selecting the blue. And this means that, hey, this vote here might still complete. So I, Alex, might still vote for blue, but if it completes and yours vote is also complete, you have a guarantee that they complete with the same value.
And
that
don't
they
have a conflict with the previous.
Yeah, you don't have conflict with Chaitanya. But like, could it be the case that, like, you know, somehow there is a conflict here? Well, I mean, theoretically this could be, but you could also say that this is not your problem, because if there is a conflict here, it means that there is also a conflict here. So it was Chaitanya who messed up. And that's it. You actually now understand consensus. So what we do as a primary for a particular vote, we talk to a majority of replicas, including ourselves. So for example, we could take like P1 and P0 as a majority. And we ask this majority two things. First of all, we ask those replicas to abstain from any further votes in previous ballots. They can still vote here, but they cannot vote here. After we receive the confirmation saying that, hey, those folks will not vote, we collect all the votes that they had cast already. And then we look at the highest ballot, which has a vote cast, and we select that value as a safe value. Using induction, that value was safe at that point in time. So let's do this here. So let's say that we are looking for a safe value here, and we have like the latest value here. We kind of like, so we know that as of this point, this value was safe. Yep. So if we pick it here, we aren't going to have any conflicts with these ballots. We kind of like might still get conflicts here, except that we actually require those folks to commit to not vote. So we have, vote, right? Yeah, so we have like blanks in here. Yeah. So therefore, we know that our value is actually safe
with
here.
Regard to everything before, but it might not result in the majority, right? That's not guaranteed, but eventually it will have a consensus. Because here you do not need to vote, right? Because you crash.
Yeah.
And Chaitanya didn't receive.
Yeah. So after we do this, like maybe someone else said, hey, actually, folks, like don't vote for Tobi. Like, and that's fine. Or like, not don't vote for Tobi. Don't vote for Tobi in this particular vote. Yeah. Because you could only like forbid voting in the previous ones, but you allow voting in the future ones.
And what do you actually mean by this particular vote? Also these votes, they're included as well, right?
Yeah.
It's basically always up to this point and before you are not allowed to vote.
Yeah. So again, this is algorithm. Like the actual consensus algorithm is you are the primary for a particular vote. Your job is to select a safe value, a value which is safe for vote, which won't give you, which won't get you personally in trouble. The way you do this is that you select a majority of our replicas, a quorum. You require them to commit to not voting in any previous votes. And then you look at the highest vote they've done so far, and you select that value as safe, which if it for some reason turns out to be not safe, you could point the finger at that previous voter and say, hey, actually, it was his fault, not mine, which is fine. There's only one case here. It might be the case that you get an empty set of votes. So let's draw this scenario. It's useful to understand. So let's say that we are like doing this one, and as a majority, you selected like yourself, like it's a natural thing to do, and like Chaitanya. So you have blanks in there, so no votes at all. Well, in this case, you could like pick any arbitrary value. It's like your lucky day as a dictator. And I mean, it might mean that like at this point there is like blue here, but still it's fine because we know that hey, blue isn't going to
reach the majority.
Yeah. And there is like you pick like red here, but what might happen next is that like Chaitanya says, hey, now actually I want to vote. And okay, let's use purple for Chaitanya. Like actually, I want to vote, and I pick me and P1, and so Chaitanya gets those commitments, and it picks blue here, and you pick red. That is still fine because when Chaitanya picked blue, it made sure that your ballot will not complete. So. Now we so this is consensus. That's it. Now let's hand wave correctness and liveness. So correctness we kind of like sort of already hand waved. If we have like let's assume that there is like I and j indexes where we get a contradiction. So let's zoom in on the j thing. When the primary for the j vote was selecting a safe value, it turned out that it didn't actually select it a safe value. Like zoom in there. Well, either this value was selected as safe because there were no previous votes in the quorum picked by the j ballot, but in that case the I ballot wouldn't select anything. So, okay, what we wanted to prove. Otherwise, okay, actually the value selected as a safe for ballot J was deemed safe in a previous ballot, say K. But then you look at I and K and say, okay, this pair actually now is also contradictory. And then you do this like induction style regression until you go to the base case and realize, hey, actually, no, this is not possible. We only can select safe values. Now let's hand wave liveness. So and that's like really easy. So let's imagine that like our consensus was running for a while and we have like a table field. Table is infinite. And while our consensus could have been running for like quite a while, maybe like 1 billion years, it was still running for some finite amount of time. So we have certain prefix of the table field, but we actually have like infinite amount of blank space past certain version. So if we have a subset of replicas which form a quorum, we have like at least 2 out of 3, we could pick any column where one of the available replicas is the leader, and we could say, okay, at this point, we will vote at that column. And that vote could complete. So no matter what is our current state, there is always a way to complete our behavior such that we reach consensus. It doesn't mean that every completion will lead to consensus. And that is actually not true. You could have a behavior where you never ever reach consensus, where like there are like too many blanks and you never reach majority. And that is kind of like sad, but it's also the famous FLP impossibility result theorem that no matter what algorithm you pick, there's going to be a certain pathological behaviors which never reach consensus. The only thing you could hope for is that no matter what place you're currently at, there is a non-pathological path out. And this is again where mathematics turns into pragmatics and engineering, because you actually want to minimize the time you are in this pathological behavior. Okay, so I would say that's it. We get consensus. Well, I guess we could, like, you know, also formally say like which messages we are going to send. Well, let's say this. So like let's think about like the actual system. So how we implement this. We have processes, and each process needs to remember two things. It needs to remember its vote in the highest ballot it voted for, and it needs to remember the highest ballot it can still has vote in. So this is okay. This is actually an important thing, like that. The state space, which every individual process needs to remember, is actually finite. So if you zoom in onto this row, it like could be as large as possible. And if we required P2 to remember the entire history, we would need like infinite amount of history for P2. But the thing is, we don't need that. P2 only needs to remember two cells. It needs to remember the rightmost non-blank cell, and it needs to remember the rightmost blank cell. And that is for every process. So now, when you are a leader, you send the message saying, hey, I'm initiating ballot number n. So you send your number of the ballot you want to initiate to a quorum of folks. When those folks receive your message, they advance their blank line to that requested ballot. And they send you the vote they previously used, unless they already promised not to vote in your vote. Yeah. Okay, so there, from a leader, goes a message saying, hey, we are voting in this ballot. In the opposite direction, from the backups goes a message, hey, yes, I will be voting in this ballot. I won't be voting in the previous ballots, and this is my latest vote when I did vote. Then you collect a quorum of those messages, you pick a safe value, and you send a message saying, okay, we are voting for that particular message. Then as a backup, you receive a message telling which you should vote for, and you either say, hey, yep, I'm voting for this one, I agree, or if in the meantime you also committed to vote in the later ballot, you just not respond. And when the primary collects a quorum of acknowledgements, quorum of votes, it says, hey, this value is selected. And it might be the case that several primaries will collect quorums of votes, but due to our trick with selecting a safe value, we have a guarantee that they all actually vote for the same value. Okay, that is it. Any questions from Tobi?
I'm good, thanks, Alex.
Any questions from the audience? Okay, so I feel like I should say some kind of an outro here, but I sadly didn't think to prepare one. So I guess that's it, and hope you found this lecture helpful. Feel free to rewatch it at half speed if you need that. And goodbye.